In the year 2025, the cosmos whispered secrets that shook the foundations of human understanding. High above Earth, the James Webb Space Telescope, JWST, a marvel of engineering with its golden hexagonal mirrors, peered deeper into the universe than any instrument before it. Its infrared gaze pierced the veil of time, capturing light from galaxies born just a few 100 million years after the Big Bang. What it revealed was nothing short of astonishing, a universe that defied the story scientists had told for decades. The Big Bang Theory, long the cornerstone of cosmology, was facing a reckoning, and the scientific community stood at the edge of a new frontier, grappling with questions that could rewrite the history of the cosmos. Dr. Elena Marquez, a cosmologist at the forefront of this revolution, stood in the control room of the Space Telescope Science Institute in Baltimore. Her eyes were fixed on a screen displaying the latest JWST images. Swirling galaxies, their spiral arms glowing with the light of ancient stars, far older and more massive than any model predicted. These weren't the fledgling, chaotic star clusters she'd expected from the infant universe. They were mature, structured, and impossibly vast, as if the cosmos had grown up faster than anyone thought possible. "This changes everything," she whispered, her voice barely audible over the hum of computers. For nearly a century, the Big Bang Theory had been the bedrock of cosmology. It painted a picture of a universe born 13.8 billion years ago in a searing, dense fireball, expanding ever since into the vast expanse we see today. The theory was elegant, supported by the cosmic microwave background radiation, CMB, the faint afterglow of that primordial explosion, discovered in 1965 by Arno Penzias and Robert Wilson. The CMB was a snapshot of the universe at just 380,000 years old, its tiny temperature fluctuations revealing the seeds of galaxies, stars, and planets. From this, scientists calculated the Hubble constant, the rate at which the universe expands, a number that tethered their understanding of cosmic history. But the Hubble constant was where the trouble began. Elena and her colleagues had long known about the Hubble tension, a nagging discrepancy in how fast the universe was growing. Local measurements, based on objects like Type I supernovae, exploding stars of consistent brightness used as standard candles to gauge cosmic distances, suggested the universe was expanding faster than expected. Meanwhile, measurements from the CMB, taken from the early universe, told a slower story. The two methods, like rival storytellers, refused to agree. For years, scientists chalked it up to measurement errors or incomplete data, but the JWST's findings were making that explanation harder to swallow. Elena's team had spent months analyzing the telescope's first wave of data, expecting it to refine their calculations of the Hubble constant. Instead, it threw them into disarray. The images showed galaxies that were too large, too structured, and too old for a universe just 13.8 billion years young. "It's as if the universe skipped adolescence and went straight to adulthood," Elena told her colleague, Dr. Rajesh Patel, as they pored over the data late into the night. Rajesh, a theoretical physicist with a knack for seeing patterns where others saw chaos, nodded grimly. "Either our timeline is wrong, or something fundamental about the universe is." The implications were staggering. If galaxies formed faster than expected, the standard model of cosmology, known as lambda cold dark matter, lambda CDM, might need a drastic overhaul. Lambda CDM described a universe driven by cold dark matter, which clumped together to form the scaffolding of galaxies, and dark energy, the mysterious force accelerating cosmic expansion. It had been a reliable framework, but the JWST's revelations were like cracks in a dam, threatening to unleash a flood of new questions. Elena couldn't shake the image of one particular galaxy, dubbed Zephyr by her team for its ethereal, spiraling beauty. Zephyr was 13 billion light-years away, its light capturing a moment when the universe was just a toddler, yet it was massive, with billions of stars already burning brightly, organized into intricate arms. According to Lambda CDM, such a galaxy shouldn't exist. Not yet. Elena felt a mix of awe and frustration. "How did you form so quickly?" she murmured, tracing the galaxy's contours on her screen. It was like finding a fully built city in a place where only villages should stand. The scientific community buzzed with debate. At a conference in Geneva, cosmologists from around the world gathered to dissect the JWST's findings. Some, like Dr. Hans Mueller, a veteran astrophysicist, argued that the telescope's data was being misinterpreted. "We're seeing artifacts, not anomalies," he insisted, his voice booming across the lecture hall. "The universe can't be that old." But others, including Elena, weren't so sure. She presented Zephyr to the audience, her slides showcasing its impossible structure. "If we dismiss this, we're ignoring what's right in front of us," she said. "The universe is telling us we've missed something big." The something big could be dark energy, the enigmatic force discovered in the late 1990s when astronomers realized the universe's expansion was accelerating, not slowing as expected. Dark energy made up roughly 68% of the universe, yet no one knew what it was. The Lambda CDM model assumed it was a constant, a steady push driving galaxies apart. But what if it wasn't? Some theorists, including Rajesh, were exploring quintessence, a dynamic form of dark energy that changed over time. If quintessence were real, it could explain why the early universe seemed to form galaxies faster than expected, and why the Hubble constant measurements didn't align. Then there was dark matter, the invisible substance thought to make up 27% of the universe's mass. It didn't emit or absorb light, but its gravitational pull shaped the cosmos, bending light from distant galaxies in a phenomenon called gravitational lensing. The JWST's images of lensed galaxies showed distortions that didn't quite match predictions. Rajesh, who'd spent years studying gravitational lensing, suspected dark matter might interact with dark energy in ways the standard model didn't account for. "It's like we're missing a piece of the puzzle," he said, sketching equations on a whiteboard. "And the JWST is showing us where to look." The telescope's ability to peer into the early universe also shed light on another mystery: cosmic inflation. This was the fleeting moment. The JWST wasn't just challenging cosmology. It was rewriting the rules of discovery. Its infrared sensors could detect the chemical fingerprints of exoplanet atmospheres, revealing traces of water, methane, and other molecules that hinted at the possibility of life. While these findings didn't directly solve the Hubble tension, they added context to the universe's evolution. If elements like carbon and oxygen were more abundant in the early universe than expected, it could mean star formation, and thus galaxy formation, happened faster than models predicted. Back in Baltimore, Elena sat with Rajesh over coffee, the weight of their discoveries pressing down on them. "What if we're on the cusp of something bigger than the Big Bang?" she asked, half joking. Rajesh raised an eyebrow. "Like what? A new origin story?" Elena shrugged, but the idea lingered. The Big Bang theory had been built on evidence like the CMB and the redshift of galaxies, but it wasn't infallible. Before the 1960s, scientists believed in a steady-state universe that expanded forever without a beginning. The CMB had shattered that idea, but now the JWST was hinting at new possibilities. Perhaps a universe with multiple phases of expansion, or one driven by forces beyond dark energy and dark matter. The tension wasn't just about numbers. It was about the structure of the universe itself. Scientists use structure formation to describe how matter clumped into galaxies, clusters, and vast cosmic webs, with empty voids in between. The JWST's images showed a universe with more clustering than expected, challenging models of how gravity and dark matter sculpted the cosmos. Gravitational lensing, which revealed dark matter's presence by bending light, showed discrepancies too. The CMB suggested a smoother early universe, while lensing indicated a lumpier one. Something was missing, and Elena couldn't shake the feeling that dark matter held the key. One evening, Elena received an email from Dr. Thomas Rice, a colleague who'd been analyzing JWST data alongside Hubble Space Telescope observations. Rice's team had hoped the Hubble's measurements might be flawed, explaining the discrepancies. But the JWST confirmed the same deviations. "There's a fundamental flaw in our understanding," Rice wrote. "The universe is trying to tell us something, and we're not listening." His words echoed in Elena's mind as she stared at Zephyr's image again. The galaxy seemed to mock her, its ancient light carrying secrets from a time when the universe was young and wild. The scientific community was abuzz with theories. Some proposed exotic particles or forces that interacted with dark matter in unexpected ways. Others suggested revising the physics of the Big Bang itself, exploring ideas like string theory or loop quantum gravity, which aim to unite quantum mechanics and relativity. These theories were speculative, untested by experiment, but the JWST's data gave them new life. If the universe's expansion was driven by something other than a constant dark energy, or if gravity behaved differently in the early cosmos, everything scientists thought they knew could change. As months passed, the JWST continued to deliver. Its images of distant quasars, powered by supermassive black holes, showed chemical compositions that hinted at rapid star formation. Its spectra of exoplanet atmospheres suggested a universe rich in heavy elements far earlier than expected. Each discovery was a thread in the tapestry, weaving a new picture of the cosmos. Elena and Rajesh collaborated with teams worldwide, combining JWST data with observations from the Euclid Space Telescope and the Vera Rubin Observatory, which were mapping the universe's large-scale structure with unprecedented precision. One night, as Elena worked late, she stumbled across a paper on cosmic tension, a term tied to the Hubble tension but focused on the distribution of matter. The paper argued that the CMB and gravitational lensing painted different pictures of the universe's clumpiness. The early universe, as seen in the CMB, was smoother, while the modern universe, observed through lensing, was more irregular. This mismatch, dubbed structure tension, suggested that dark matter or gravity, or both, behaved differently than models predicted. Elena felt a spark of excitement. "This is it," she told Rajesh the next morning. "The JWST is showing us the universe's adolescence, and it's messier than we thought." The journey wasn't just about data. It was about the human drive to understand. Elena thought of the generations of scientists who'd puzzled over the cosmos, Einstein, Hubble, Lemaitre, who first proposed the Big Bang. Each discovery had built on the last, challenging old ideas and sparking new ones. The JWST was their legacy, a tool to ask questions they could only dream of. Yet it was also a reminder of how much remained unknown. Dark energy, dark matter, inflation, the nature of gravity. These were pieces of the puzzle that didn't yet fit. As 2025 drew to a close, Elena stood outside under a star-filled sky. The universe felt closer, yet more mysterious than ever. The JWST had shown her a cosmos that was older, stranger, and more complex than she'd imagined. It challenged the Big Bang, not by disproving it, but by demanding a deeper story. Was dark energy evolving? Was dark matter more dynamic than thought? Or was there a new force, a new physics, waiting to be discovered? Elena didn't have answers, but she had questions, better questions than ever before. The universe was speaking and humanity was listening. With each new image, each new spectrum, the JWST was unraveling the cosmos' secrets, one light year at a time. For Elena, Rajesh, and scientists everywhere, the journey was just beginning. The stars above seemed to pulse with possibility, and somewhere in the depths of space, the truth was waiting. Back in the control room, Dr. Rajesh Patel was hunched over his laptop, his fingers flying across the keyboard as he cross-referenced JWST's latest spectra with models of early galaxy formation. The telescope's infrared eyes had captured not just images but chemical fingerprints, traces of heavy elements like carbon and oxygen in galaxies that shouldn't have had time to forge them. "This isn't just about Zephyr anymore," Rajesh said, his voice tinged with urgency as Elena rejoined him. "We're seeing these signatures across multiple galaxies. The early universe was a factory for heavy elements, and our models can't explain it." Elena leaned over his shoulder, studying the spectral lines on the screen. The data suggested that stars in these ancient galaxies were born and died at breakneck pace, fusing hydrogen and helium into heavier elements far faster than the Lambda CDM model predicted. If star formation was this rapid, she mused, then either the universe is older than we thought, or something was accelerating the process, something we don't understand. Rajesh nodded, his eyes narrowing, like a catalyst, maybe a new kind of particle, or a tweak to how dark matter clumped. The idea wasn't new, but the JWST's data gave it weight. Dark matter, that invisible scaffolding holding galaxies together, was a cornerstone of cosmology, yet its nature remained elusive. Scientists knew it exerted gravity, bending light through gravitational lensing and shaping the cosmic web of galaxies, clusters, and voids. But what if dark matter wasn't just a passive framework? What if it interacted with baryonic matter, ordinary stuff like stars and planets, in ways no one had modeled, the JWSTs?